So, and this is a joint work with my colleague Paraskevas Papanikos, the PhD student Christina-Margarita, and PhD candidate Louka Eleftheria-Sotiria, dealing with the numerical simulation of corrosion attack in aluminum copper lithium alloy 2198. About motivation, so previous to the, just continuing to the previous presentation, there are different design criteria for each different case in aluminum structures. You can see there is damage tolerance, yield strength, modulus of elasticity, but oops. The most difficult part with this kind of material is aging, because just like human beings, also aluminum alloys age. So, and they age by reducing their mechanical performance, but they also introduce some precipitates at their microstructure. So something like, we call it artificial aging, simulating natural aging. And you can see these small precipitates of the order of magnitude of nanometers that block, that hinder the dislocation movement, and then altering the mechanical performance. But I will now switch to the damage problems. As you can see, just to figure out what are the difficult situation in aircraft structures, there is fatigue, there is corrosion, and there is impact damage. In this case, in our case, we will try to simulate, this is, I think, this guy, Ad Vlot and Fossila, comes from TU Delft many years ago. So we will deal with corrosion. That is mainly one of the top problem in aircraft structures. So we have the problem of pitting corrosion. As you can see, it grows below the surface, and you have, this is a cross-section of corrosion, and reduces the thickness of the material. Plus, there is also some below hydrogen embrittlement below the corrosion products. And this is such a case. Here you can see the pit, and below at the subsurface, you have hydrogen embrittle area. And as you can see from the publication, this is not new. Hydrogen embrittlement in metals and in aluminum alloy is not new, but we are trying to figure it out how this happens to the new aluminum copper lithium alloys. So this one goes, we checked the two different tempers, T3 and T8 commercial tempers. The T3 is more flexible, more plausible, and having more plastic deformation capabilities, while T8 has more strength capabilities. So typically metallographically, and just to see the cross-sectional, and then also perform some metallographic analysis. So we have used this EXCO, exfoliation corrosion, according to the standard. It's a very aggressive corrosion electrolyte. For example, after 2 or 4 hours, you have a decrease in tensile ductility more than 20–30%. While with sodium chloride solution, you need something like 3 months to get this kind of tensile ductility decrease. These are the results of the tensile test, as you can see, for the T3 temper and the T8 temper. It's a pity the lady from Romania to discuss about is missing to discuss about some effects on the uniform elongation, but never mind. So this is the experimental work. So in the microscope, we had several cuts, and we measured with a microscope the maximum depth of attack. And there I will show you the evolution of the crack depth versus different EXCO exposure time. We have selected in this publication a small one, 2 hours, and excessive one, 24 hours. So these are the crack probability density of 2 hours. So you can see there is something like a distribution, something like a normal or log normal distribution of the cracks for 2 hours. And for 24 hours, as expected, the probability density goes at higher classes of corrosion attack. We have duplicated the same things on T8. Let me remind you that T8 has different microstructure, more precipitates. So the probability density of the crack are different when compared to the T3 temper. And for a higher exposure time, then as you can see, the peak is around 100 microns. On the contrary to the T3. So the next case was the surface. We have checked the small hours. As you can see, for the T3 you have no pitch, while at the T8 you have more pitch. According to our expertise, you have more distributed pitch in the surface, but not well at going to the depth of the material. And of course, these are the tensile test results for different hours, showing that you have not significant stress decrease, but you have a significant tensile ductility decrease. And we have duplicated this on T8 temper, showing that as you can check, if you can compare the two tempers, you will see that T8 seems to be more corrosion resistant than the T3 because you have less tensile ductility decrease. Regarding, I will skip this. I will now move to the finite element that is more sexy to give you. We have modeled only the 1/4 of the specimen, and we have performed elastoplastic analysis with a displacement set corresponding to 0.4 nominal stress. And the stress was calculated from the reaction force in the loading direction. And as an output, we have the stress strain curve. So this is the full mesh. We have used a triangular mesh, and these are the outer surface mesh. Actually, it's a random mesh, having something like circular or elongated dents, actually, ellipsoids. All this is random, and the area of the dents was simulated according to the photographs that we had from the top surface. So here you can see this is 2198 at 2 hours EXCO. So initially, this is it, and if you apply 8%, then nominal strength, then with gray area you have something like you see that the damage area is elongated. With higher nominal strain, the damage area is more expanded, and here it's actually when we actually stop, when all the damage area is unified, and then we have something like damage all over the width. This also goes for a 2198 T8 temper, again for 2 hours. if you can remember, again, this is a random one. If you can remember for the previous T3 temper, we had something like 16%, now we have only 10%. Just to address this. And of course, just for comparison purposes, this is the same T3 against 24 hours EXCO. Different, as you can see, different, quite random, and different paths for equivalent failure. And of course, this is the similar for 24 hours EXCO of T8 temper. And okay, and these are the results. For example, as you can see, we can highly calibrate the FEM model. There is not significant decrease in the stress strain curve. For 2 hours, it's highly, the results are really close. While for the T8 temper, we cannot prognose the area after the uniform elongation. That's why we stop until the end of the uniform elongation. For higher corrosion times, the prediction, the calculation are less accurate because of the higher degree of random of corrosion. Of course, the lowest the corrosion is, the highest the accuracy in prediction in this. And in this regard, this is something like a preliminary study with Professor Papanikos, and we intend to extract this with different other parameters, for example, to introduce also not only the surface area, but also to the depth of attack and for different other exposure times. But these are the preliminary results, and we expect to conclude and have a normal publication in due time. Well, thank you very much for your attention.